Thanks for coming, everyone. I'll try not to bore you. Yeah, I'm going to be talking about hydrology, land cover, and land use change in the semi-arid West. So what does semi-arid mean? What's the water cycle like? How has the landscape changed over the last 250 years? Quite a lot. And the case for rehydration and resavanization. So what does that even mean? So let's jump right in. So the four main topics I'm going to cover is the Mediterranean climate, which we enjoy here, hydrology, kind of how it works, land cover and land use change, and restoration and rehydration, like I said. So there are 5 places on the planet where we have Mediterranean climates. Mediterranean climates are hot, dry summers and cool, wet winters. So the 5 are southwestern Australia, western South Africa, the Mediterranean basin, of course. And you can see that it's just like the top of North Africa, a little bit over here, and then in the Middle East, a tad, all of southern Europe, and then California and Chile. So what makes a Mediterranean climate? It's generally a westerly facing continent with a big body of water. And that's what creates the conditions for the cool, wet, and mild winters and the hot or mild, dry summers. Everyone knows it doesn't rain here for 6 months, so we need to get our water from somewhere. So, in terms of land cover, the Mediterranean basin takes 60% of the overall Mediterranean climate land cover. South Africa is the smallest with 3%, and it's been a Mediterranean climate for millions of years, so it's developed unbelievable biodiversity. The proteas are a pretty good example if you're familiar with those. California's 10%. Yeah, and in the Köppen climate scale, that is a climate model that has it's broken down into 5 groups, 6 groups, excuse me. Mediterranean is within the temperate, mild winters. Yeah, and so the Mediterranean climates can be broken down into 3 different groups. You've got hot summers, moderate, and then cool summers. So what I tell people when they ask what the weather is like in Morro Bay, I say it's extremely mild, which is a bit of an oxymoron, but nevertheless, it's cool. So it's less than 70 degrees year-round average. So it's, once you get into the 60s, you start to kind of get chilly. You look to cover your neck. So Sacramento, Los Angeles is a CSA. CSB is Santa Barbara, Long Beach, Santa Rosa, and then a CSBN, and N is German, because Köppen is German, stands for the word fog. And that's the coldest of all the Mediterranean climates. It's still not that bad. You can still grow avocados. What makes a semi-arid climate? Well, according to this scale here, at 11 to 12 months is very arid, 9 to 10 of drought, 9 to 10 is arid, and 7 to 8 is semi-arid, 5 to 6 is subhumid. So we have a drought of 7 to 8 months. And here's an example of Morro Bay, California. This histogram here, you can see that our temperature averages around, in our lowest temperature is 50 degrees, which is pretty cold. Not if you're a plant, but if you're a warm-blooded human, it's a little cold. Southern Portugal in the Algarve is about 10 degrees warmer on average. So it's a bit nicer if you're a human, again. But these unique climates have created our amazing biodiversity in California. So gotta be thankful for the chilly air. What you can also see here is so this is depicting two things. One is the precipitation. So it's roughly 4 inches of rain in January, you can see here, and then this is the drought, so the typical summer drought, and then this is the temperature. So this window right here is the summer drought, and that is typical of a histogram of a Mediterranean climate. And please jump in if you have any questions, because some of these can be sophisticated graphs. What do we have here? Well, this is 140 years of precipitation charted by Cal Poly. What do you notice? You notice a lot of ups and downs, and this is annually. So from one year to the next, you could have a huge rain year, or you could have a drought, and you could see examples of really big rain years, followed by which is average. So Cal Poly gets roughly on average 24 inches of rain a year. So some of these peaks are just huge. They're way above average. This is the 22-23 rain year. I'm sure everyone remembers where they were. Morro Bay flooded. I know there was flooding here. It was a disaster. So this is common. This is typical in Mediterranean climates, and we're going to get into why in a second. But this is what I like to call the drought and deluge cycle. So people ask you why you live in California. You say, well, the drought, the floods, the fog, and fires. It's not all doom and gloom, though. So this is a evapotranspiration zone map of the state of California. I like it because it helps to wrap your head around, why do we get floods? Well, certain areas will get a lot more rain than others. There's orographic differences. The mountains will trap a lot of water and send it down our waterways. But you could see that the coastal plains and the heavy fog belts are the zone where we live in, and it has its pros and cons. This is Morro Bay right here. So Morro Bay, the estuary, San Luis Obispo. So let's see, this is Avila, so we're right around here. So we're back in this zone 1, but you see there's a little window. So a lot of microclimates, as we know. And the thing I wanted to point out is the evapotranspiration. So the amount of evaporation that's happening in December, January on a monthly basis is very little. It's about 1/2 inch. And then you get to the middle of the summer, and it's significantly higher. How much higher? It's about 6 times higher. So that means when you have big rain events in the winter and really cool climates, the water normally would evaporate, but it can't, so it sticks around, and that's why flooding is common. It's part of, there's only so much water that the land can absorb. Once it's saturated, it's not evaporating, so we get floods. And this is an example of the flora that is a result of this water deficit. Here is another histogram. You see these quite a lot in travel books, for example, to get a sense of temperature and rain, like Lonely Planet. And that water deficit is what created this lovely oak woodland ecosystem, coastal prairies, chaparral. Like I said, we're a biodiversity hotspot, and it's because of these really unique conditions that we have. The Mediterranean climate is only 2% of the Earth's surface, so pretty lucky to be here. Anyone recognize that? This was after the big rains in the Tulare Lake, which had disappeared for over 100 years, I think. For a long time, I don't know the exact date. But all the snow pack melted. An area that at one point, Tulare Lake was the biggest body of water west of the Mississippi. Was then, over the years of agriculture, drained through groundwater pumping. And then last year was back, and then I'm pretty sure it's mostly gone now. So it's pretty quick. The evaporation is really high in the summer, and things go even faster if you are pumping the water and using it for crops. And when you spread it out on the landscape, trees suck it up, the sun hits it. So, and that is the hydrological cycle. So there are 10 steps to the way that water moves around our planet, right? We start with evaporation. It's sent up through evaporation, through transpiration, and sublimation. It goes into the air, it condenses, it's transported through clouds, and then it rains. This is an example of the orographic conditions that we have in California, because we have a lot of coastal ranges that take the transported cold air and they force it up to where it's colder and it condenses, so we get much more rain in the mountains, twice as much as we do on the coastal valleys. And yeah, and then it is deposited, also known as rain, infiltrates from the surface water into the ground, and then through the ground we call it percolation, and then it's taken up by plants and the cycle starts over.
May I ask the sublimation?
Yes.
What is the sublimation process?
Sublimation is water is vaporizing off of snow and ice, and it transitions from a solid directly to a gas. What do we have here? This is an image of the topography underground. It's a subterranean topography, or a bathymetry. I can't remember if bathymetry is just for lakes and bodies of water. But this is the city of San Luis Obispo, and this is the groundwater basin. And what you can see, here's a cross section. You can see that there are in fact subterranean mountains. And so, you know, right here, this is a bedrock divide, right? So that's this point right here. So in fact, the water, the basin is divided by these two, the underground mountain range. It's pretty cool. Mm-hmm. Pretty neat stuff, kind of not that hard to conceptualize if you just imagine there's another topography underground, right? So when the water does infiltrate into the ground, where does it go? It continues to flow. Water is constantly moving. And, you know, it'll reach the bottom here, and it's kind of an underwater ocean, but it will move in a certain direction, just like it moves across the landscape above ground. And so there is a flow above and below ground, and that's something we want to keep in mind. So we look at this image and we see, okay, this looks like summer in California, but so does this. Does anyone know where this is? This is Laguna Lake in San Luis Obispo. Here's another great example of mostly freshwater body of water. And so what's happening is you have this interplay between surface water, in this case the Laguna Lake, and groundwater. And this lake is being fed by streams above ground, which we can get into afterwards. But it's also being fed by the water that infiltrates into Cerro San Luis. It's infiltrated in and then slowly will seep through fissures in the bedrock and slowly make its way out over time. And so this interplay is important when we think about how much surface water there is, how much groundwater there is. They are related, especially when it only rains for half the year. So the water hits the surface. It's aided by plants and roots into the ground. It'll also flow off the surface, and it'll arrive at a perched water table, for example. So there might be like a clay pad here that's not allowing the water to go down further. It's percolating. In some cases, it'll surface, and here's the main water table. You see it's actually connected to the creek. So there's an interplay is kind of the point when we think about where the water goes and what it's doing. And here's another cross section of a riparian corridor. We've got the aquatic habitat in the zone in the middle, the riparian zone, the ecotone where the two areas meet, where the riparian and the upland meet. So that would be, for example, willows and poplars and sycamores. These are tule grasses and sedges, and then you can get up onto the water, onto the upland, disconnected from the water table, drought-tolerant plants. And then, of course, you'll also have oak trees and other what they call phreatophytes. But basically, it's a tree that's tapped into the water table, but at a much higher level. That's the adaptation of the oaks. So we have ecosystems that are dependent on this interplay between surface water and groundwater. Here are some examples: marshes, riparian ecosystems, seasonal wetlands and springs. They each have their associated plants and animals as well. And because there's only a certain amount of water in California, and certain species and ecosystems depend on it, a lot of those are threatened. These are some of the fantastic creatures that you'll find in these groundwater dependent ecosystems. Western pond turtles are threatened. Steelhead trout are threatened. Those are, of course, a keystone species, which means that a lot of animals and plants rely on this, the nutrient cycling of these species to live in their life cycle. California red-legged frog, a lot of really cool, unique species. So that's hydrology. Now I'm going to talk about land cover and land use change and how that affects the hydrology that we all rely on, as we all need water to survive. So this is a great book. I brought it with me if you want to check it out. It's called A State of Change by Laura Cunningham, The Forgotten Landscapes of California. She's an environmental illustrator, studied a bunch of historical ecology, and painted these forgotten landscapes that have changed over the last several hundred years during settlement. So this is Pasadena, 1,000 years ago. Engelmann oak savanna, one of the cool, unique oak species endemic to only California, threatened, and some neat native grasses, perennial and annual. This is Pasadena today. Not that different. And that's okay, you know, we're living in the present. You can't change the past. You just learn from it. Of course, there are a lot of paved surfaces. So where there are paved surfaces, there's no infiltration. This is the Santa Maria River Valley. You could see there isn't a piece of vegetation in the channel. This is after an image after, I cherry picked this, after the floods of 2022, 2023. But what you can see is how close the agricultural fields are to the channel. A big river wants to meander a lot. So when we are in the decision-making capacity, we want to ask ourselves, how much room do we need to let this river meander? What's the future going to look like? So these are kind of questions when we're developing that we want to ask ourselves. This is the LA River. Not much infiltration in this concrete half pipe. I think those are the reservoir dogs down there. This was a response to a flood in the 1930s, and the city of LA decided to pave in the entire stretch of the LA River. And now they're having some issues with that because people have developed right up to the banks. There are a lot of marginalized communities, and you'd have to displace a lot of people to give enough room for the creek or river to be itself. So before we develop, we want to ask a lot of deep questions about what our goals are and what the needs are of the place already. These are just some examples of how California's changed over the years. That's the first mission in our region, Mission San Miguel, 1770. So what did that bring? Well, it brought a totally different worldview, different economies, tilling on a broad scale with metal tools, cutting down of trees, agriculture. This is a more recent image from the area where I live in. So, the land was not tilled for as long as humans have been here in California, over 10,000 years. And then in the last 250, there were a lot of changes, right? So had to remove all of these plants and trees that once took root there as the economy changes. Here's another example. This was the charcoal industry, specifically in Adelaida, but it was everywhere before we had access to fossil fuels to heat and cook and support ourselves and our economies. So a lot of trees. This was before CEQA. So so these changes happen to the landscape. This is from tending the wild, and those are the remaining area of habitat. So freshwater wetlands are at about 10%, and coastal marshes are at about 30%, but here's some other examples. Old growth coastal redwood forests are at 5% of their original extent. So a lot has changed. Native grasslands are at 5%. The ones that are the most economically interesting are the ones that change the fastest. Those are the flat areas near creeks and rivers. I highlighted those two because we're going to talk about it in a second. Why there's more coastal salt marsh than freshwater wetlands. You can think about that for a second. So how do we find out what happened if we don't have pictures, we don't have journal entries? We can use sediment cores. This is the closest thing we have to a time machine. It's pretty awesome. You basically dig a core into the mud of an estuary, you pull it out, and then you line up the markers that you see with events in the past that you know happened. I'll show you in a second. But the point is what this article demonstrates is that there was significant land cover and land use change, especially with livestock and agriculture. and that greatly increased erosion and reduced trees, arboreal taxa. That's the message. So this is where the cores were done. Here's Dockside Cafe. Choro Creek, Los Osos Creek, those are the cores that were dug into the ground. So you take out this core, you say, okay, what are the markers of this depth? All right, it looks like, in 1975, we were using a lot of lead in our gas. And if you look here, you see, oh, there's a bunch of lead in this strata. Okay, line that up. Okay, what else? And so that way they can figure out more or less the time frame, and then you can see what's in these strata, and you can determine what the landscape looked like before changes and way back into the past. So this goes back 1,200 years. It's pretty cool, if you ask me. The Spanish arrived in 1769. The Spanish mission was 1770 and 1772 in San Luis Obispo. This is from the Choro and Los Osos watershed, this project. And what you see, we'll get to it in a second, but the arboreal taxa all decline. So in some cases they go up, but then they quickly decline. And that was because of the new economies that were brought to the landscape. And the one that I always point to is the native peoples of California. 50% of their diet was acorns. And so this is Puercus's, our oaks, slowly increasing, the Spanish arrive. So there was a big drop off in pollen in this sediment core, which we can infer means that the oaks were removed. We think about the economies that the Spanish brought. They brought grazing. You'd kill the animal and you would tan its hide. You would use the oaks and the tannin-rich bark to tan the hide, send it over to the old country. So this is an example of a map of, here's more rock. You can see there's no bridge to the rock at that point. This is from 1897. And this is the extent of the Morobe salt marsh. So the salt marsh is a very shallow marsh that has salt water in it, and there's, I don't in fact know all the plants that grow in it, but I think it's eelgrass. I could be mistaken. But you could see its extent in around 1900, so it's this kind of tan color here. And then the red marks the current salt marsh. So in about 120 years, that is an increase in erosion from these two twin watersheds. And here are some pictures. This is a picture from Santa Barbara aerial photography from 1937, right before there was the war effort, and they developed the Embarcadero, and this is today. So what we do know is that our land use and our land cover, our fluctuations in dry and wet, the stocking amount, a lot of reasons, is creating a ton of erosion in our gem of a water body on the Central Coast. But I would argue is the coolest one on the West Coast. But yeah, here again, you could see 1937, 2020. This could be at a low tide where it looks worse than it is, but it's significantly more. How much more? The Morobe National Estuary Program is determining that, and it was also deduced from the work of the mud cores, because that was another thing they did, is they tried to figure out, well, what is the erosion rate? And what they determined is it's about 8.8 millimeters per year, so about a centimeter a year. And so then you have have to ask yourself, okay, well, that's the current rate. Well, what was the baseline rate? And what they determined from the sediment core study is that it was about 2 millimeters a year. So that means that we're at 4 times the erosion rate of the past. And that's why this area is filling in a lot faster. So, why is this happening? What can we do about it? What did the old landscape used to look like so that we can try and figure out how to restore it, right? We, in restoration, we talk about restoring to what? We do, the Morro Bay National Estuary Program also considers the sea level rise as an important factor to keep in mind when we are talking about erosion. So if the sea level's coming up and the mud is coming up, there is actually a little benefit to having the mud flats be higher. So this is what we're working with now. But yeah, so what did the landscape used to look like? Well, we didn't have livestock. We didn't have barbed wire until 1900. So it used to be wandering elk. There were a little bit in our region, they were mostly on the edge of their ranges. They were in bunch grass, chewing on bunch grass on their cud. That would percolate, or infiltrate in and then cause a spring, would run over the surface. It was a forested hillside that would also absorb the impact of rainstorms. The leaf duff would hold that together. Then the banks were held together by big trees, and the aquatic ecosystem was mostly intact. Today, and this is not putting the blame on anyone, this is just what we have to deal with. We have fixed paddocks with livestock that are sometimes overgrazing. Because of that, the cowpaction, as they call it, has created a very impermeable surface. There are no bunch grasses with deep roots, so there's hardly any root system. So the water hits the ground and runs off. It runs off, it increases in velocity, and it can cause sloughs. There are no trees to absorb the extra water or the rainstorm. So there's, just this velocity just keeps going faster and faster. There's no infiltration. It comes to a destabilized bank or an impermeable bank if it's developed, and the sediment fills the channel. And this channel that used to have almost, runs of steelhead that people would pull out 3-foot-long fish in the winter, has little rainbow trout like this big now. They're still around, but so it's the question of what do we do with our aquatic ecosystems. I think it starts up here, and it's really throughout. But this is a great example. I can't recommend this book enough. This is the estimated historical elk distribution beforehand, although archaeological research and digs have not turned up many elk bone or other unique grazers. It's mostly deer in coastal SLO County. They were mostly over the coastal ridge, but they were around. Then the populations dropped precipitously to the 1970s. That's all that was left of the 3 different kinds of elk: Rocky Mountain, Roosevelt, and Thule. And now we're restoring some of the populations. So there are a lot of great stories we want to be celebrating, like the condor, for example. But a big part of this is the economic model that's driving this overgrazing of our landscapes, where we can't allow bunch grasses and perennial plants to cover the landscape to reduce the impact of rain events and increase infiltration. And Mediterranean plant species are adapted to summer droughts, right? So they have these super thick, fibrous root systems. They have a deep taproot that grows down in the beginning to survive the drought, and then they have these lateral roots to capture fog, moisture, and every drop of water that they can. So when you remove those from a hillside, you remove the anchor, and the hillside can fall apart. Here's an example of a redwood tree that has a lot of lateral roots that will send roots to the surface to capture the fog in the summer. Up to 20% of the water from a redwood forest can come from fog in the summer. So when you remove the vegetation on a landscape, you're also removing water in the summer in the ground. And so how do we return the vegetation to the landscape within our current economic model? This is just a great image. Big Sur in the 1930s, they cut that road through the most popular road, arguably, in the United States. But this was also before there were a lot of regulations, and a lot of watersheds were altered. Best management practices were not necessarily used every time. So because of all of these factors, including human physical changes with machinery, we have these runaway feedback loops. This is an example of a creek near where I live, and it's got a 35-foot creek bank that's eroding periodically during high velocity rains because there's nothing slowing it down. And this is from the creek bottom. So how do we slow this water down? Well, it takes a lot of watershed-wide work, but the creeks are slowly trying to meander. I talk to folks that say that 25, 30 years ago, they would put their tractor in the creek bottom and push the willows out of the way. And part of it's good. You do want to remove some of the debris so that there aren't debris jams. Maybe not with a bulldozer. On to restoration and rehydration. So what do we do about this predicament? Well, these guys are great rehydrators. Returning them to the landscape beaver would be excellent. They were removed in this incessant push for wealth, even before the gold rush. Otters, beavers, abalone, there are a lot of fallen comrades in the story, but we can work to return them to the landscape. So when we think about managing a landscape, it's good to think about where things go and how natural systems work. So this is Yeoman's keyline scale of permanence. On the x-axis you have relative permanence and time on the landscape, so how long it's going to be there for. And on the y-axis you have how difficult it is to make the change and how much energy it takes. So the longest it's going to be on the landscape and the most difficult to change is the climate. Then you have the land shape that requires heavy machinery. Then you have water. So these are the things that we want to tackle first when we're designing our spaces that we inhabit, right? And then as we get further down towards easier to change and less time on the landscape, you can cut a tree down. It's a lot easier to cut a tree down or to remove a fence than it is to change the shape of the land. So it's good to keep this in mind when we are thinking about how to design the built environment. What is rehydration? So we have a parched landscape with not nearly as much infiltration. How do we restore the aquifers? How do we slow down this water that has huge velocities running off the landscape? So rehydration is a way to do that, and it's basically diverting water to slow it down for one of several goals: flood control, sediment capture, aquifer recharge, habitat restoration. Some examples of this, and this is just on the farm scale. There you can apply this land management to anything, to a city, to a town, to a farm, to a backyard. But the one that I'm going to talk about is the farm scale. And a really great practitioner, Mark Shepard, wrote a book, Restoration Agriculture, where he blends restoration and agriculture. And he uses a design system that's based off the keyline system to manage water, to increase infiltration, to use it because plants need water, and it also reduces erosion, it creates habitat, it has a lot of co-benefits to it. So this is an example of my family's project to reduce runoff water, to slow it down, and to sink it into the ground. You hear slow, spread, and sink, the 3 S's. So that's one way that we could do this. You'll hear a city talking about this as a stormwater capture. But in a farm, it has a different name. But yeah, basically we take the runoff from the hillsides and we capture it in a series of landscape features to sink it in, and it has a lot of co-benefits. And this is the bottom of the system. We've planted native pollinator species, and it's pretty nice too. So the first part, so that's rehydration. How do we rehydrate the landscape, at least at the farm scale? And the second one is restoration. So what is the ecosystem that we live in? And in California, you can depend a lot because there's a lot of microclimates and different unique ecosystems. And the one that I'm focusing on is the California oak woodland. It is one of the most biodiverse. 300 terrestrial vertebrates, 1,100 native vascular plants. You only need 1,400 to be a biodiversity hotspot, so that's pretty close already just there. And a ton of fungal communities and insects. But look at all these charismatic fauna. So coming near the end here, so restoration agriculture, you determine what your ecosystem is, and then you mimic it, biomimicry. So we chose the coast live oak woodland. What are the interesting and edible genera in this ecosystem? Well, we've got oaks, which of course have edible acorns. We've got stone fruit, prunus, elderberry if you have a cough, grapes if you want to be merry. Amelanchier is in the apple family, but the list goes on. Rosaceae, rose, so there's a ton of native plants that are fully adapted to this drought, summer drought. Walnuts. So when we think about developing our and restoring our landscapes, and we think about how to produce food, which is one thing that we all need, I like to just imagine what could we eat from, what could we make wine out of, what could we use, and this is an example of what's it called? Bishop Peak? No, Hollister Peak. Sorry about that. Hollister Peak. You could see this is a north-facing slope, so it's covered in chaparral and oaks. You get down onto the flats, and then you look at the south-facing hills, and it's nothing but grass. But I imagine that the landscape once looked more like the oak savannas of Pasadena, And when you visit other places that are also Mediterranean climates, this is Portugal. It's a photo that I took of a oak woodland landscape. And there are a lot of questions to why we don't have any more trees on the landscape. We were able to determine that from the sediment cores, that there used to be a lot more. But they have tons of benefits. They're compatible with our current livestock practices. So how do we incorporate them back into the landscape because of all the great benefits they have? Sequestering carbon, reducing feed costs, reducing soil erosion, obviously a big one, because oak trees create their own soil around them, and that's one thing that we are running out of, especially in the Morro Bay estuary watershed. So here's one way we could do it, through cow cages. And they're compatible with current grazing practices. So we need to start thinking outside the box when we see all of the issues with our current system, and all of the benefits that are possible from putting a tree back, putting perennial plant back to increase water infiltration and restore habitat. And that's all. That's a little oak tree. Thanks very much for listening.
Thank you.